This project started to build a long-range tracking device for drones. Here I have an Egg Timer Mini attached to a 7.4-volt lithium polymer battery. The Mini includes a Maestro A2135 GPS receiver, the beige box, and a specially configured HM-TRP OPRF transceiver module. The transceiver transmits at 915 MHz to a second HOPE-RF module. The NMEA data received by the second transceiver, EggFinder RX, is sent through the white wire from the RxD pin to an RX pin on a yellow board containing an Atmega 328P, which is basically an Arduino Uno. The green blinking LED on the EggFinder RX and the blue blinking LED on the Arduino indicates data packets being received. This data then proceeds via UART connection to a 2102 UART USB bridge, where it ultimately is received as a serial connection on a laptop. The signal transmitting the NMEA data is ultimately a voltage oscillation, so it can be visualized with the dimming and brightening of an LED. When I visualize the data on the laptop through the serial connection, I see question marks. I do not recall exactly what I did. Perhaps it was a misconfiguration of the baud rate. Basically, the expected time to send a packet on the serial connection did not match the actual time. Typical values of this are 9600, 115,200, etc. Could have also actually more likely been the length of the buffer memory specified to hold the MEA data as it comes in. Or both. I believe I used a simple test example with the tiny GPS library to ultimately read in the data. Some of the code for it isn't on the right. I used the RTL SDR to receive FM radio signals. I was also able to transmit to the RTL SDR at 915 MHz using the Lime SDR Mini. You can see the spectrum plot, the rapidly moving white jaggy lines at the top, and the colorful spectrogram, or waterfall, at the bottom. Here is the GNU Radio companion sketch for the FM radio transmission provided by Myriad RF for the Lime SDR Mini. I thought that I was going to configure the Lime SDR Mini to send my LoRa data, but it ended up being much easier to use the LoRa devices provided by Heltec Automation. I have the ping pong example using two Heltec cube cells transmitting over LoRa. Here I am visualizing LoRa transmissions with the GQRX software and an RTL SDR. I also have two Heltec modules that combine both Wi-Fi and LoRa. Both of these can receive signals from the cube cells and can serve as a bridge to a Wi-Fi network. Using one of the provided examples, the simple Wi-Fi server, I am testing the Wi-Fi capability of the Heltec Wi-Fi LoRa ESP32. Two white Heltec LoRa Wi-Fi ESP32s are receiving from a green Heltec LoRa cube cell dev board. In this example, I ran the default LoRa sender code example for the Heltec cube cell dev board. Make sure that the set frequency is 915 MHz, not 868 MHz or something else. This is for the US. The allowed frequency for these IoT type devices varies by region. This is a BH1750 digital light sensor on a debug board, both provided by Heltec Automation. To hook it up, I followed the pinout as well as the silk screen on the board for the Heltec cube cell linked to earlier in the video. At first, I had the cube cell connected directly to serial for debugging, and then the BH1750 on the Heltec cube cell is transmitting to the Heltec Wi-Fi LoRa ESP32. The Heltec Wi-Fi LoRa ESP32 is connected via serial to the laptop, so the Wi-Fi capability is not being used. I can put my hand over the BH1750 digital light sensor and see the number change on the OLED display on the Heltec Wi-Fi ESP32. Combine the BH1750 test.ino with LoRa sender.ino health tech code examples with modifications to send the sensor data over LoRa and run them on the cube cell. Take the OLED receiver code example and change the band to 915 e to the 6 or 915 MHz. I can extend the OLED receiver code to write the sensor data to a web server accessible by laptop. Unfortunately, the data is only updated when I do an HTTP GET, so this will be redone with WebSockets later. To test writing the data to a database instead of the browser window, I set up a PHP script that takes whatever value of lux a user passes as an argument to an HTTP GET and writes it to a MySQL database. I think someone from the Techlahoma Slack mentioned WebSockets when I wanted to continually get data from the sensor as it was available. The Abley article, linked to below, mentions, in my words, WebSockets as a means to maintain a full duplex persistent connection between two agents after an initial HTTP handshake until connection is closed. The example you are seeing above is from Sean Heimel. The black box has output from a Python client in the example. The interaction with this and the browser WebSocket clients will be apparent in the dev TTY USB 0 serial output. This is the second example from Sean Heimel, which involves blinking of an LED with a WebSocket server. Unfortunately, the code has no way of checking the state, only remembering what happened, so it must be modified. WebSockets are better than HTTP GET used earlier, which makes a request, but then closes receiving no more data. This is why I had to refresh the browser whenever I wanted to see new data. In reality, I wanted to see new sensor data whenever there was new sensor data. The blinking LED example also involved a soft access point, which meant it was not on my router's network, but I was able to modify it so it was. Here is the device, and following, here is the code that I had for that. Around this point, I realized that this approach was not going to give me the data from a sensor if it was realized in place of the LED, because I was pushing commands to the device rather than pulling information from it. When I thought of two-way communication, I thought of a chat app. Thankfully, WebDev Simplified offered a version with Socket.io that I was able to follow and build. The browser acts as a client, and code is written on the server in such a way that messages sent by any client are broadcast to all. I did like this since I could see a sensor in place of sending quote-unquote chat messages. Unfortunately, it used Socket.io, which I found was incompatible with standard WebSockets. I continued looking for examples I could easily modify to aid my weak understanding. I then started looking for WebSocket clients and servers for the Arduino platform. I found Tech Tutorials X. It offered both a client and a server that would test and work together. I tried getting Marcus Settler's Links 2004 library to play with Morganser's ESP8266 WebSocket library. I was getting errors with running Marcus's code. Moreover, it was generally a bad time. I learned 0.0.00 where IP address was bad. Following the stack trace tells me about issues with the WebSocket loop. Removing this removes complaint, but fixing it requires a few more lines of code that will be showing next. It turns out that I was setting the code up incorrectly. On the server side, I see connecting to Wi-Fi, connected to the Wi-Fi network, 10.0.0.8, calculating, sending. Then comes the client. This is one crazy Marcus client. Then I get a bunch of random numbers from the client. Here's the server-side code. On the client side, when I fix my code using Marcus library, I see connecting ... connected, my IP address 10.0.07, random number is 909, random number is 22. I can begin transmission of LoRa packets with the Heltec Cube cell. I can modify the WebSocket client on the Heltec LoRa ESP32 to receive the LoRa packets and forward them to the WebSocket server. I can visualize the data in the serial connection accessible by the Arduino IDE and through the Python REPL as suggested by the 4 ways of communicating with serial port in Linux video. Here's a LoRa and WebSocket client code running on the Heltec LoRa ESP32. The WebSocket server code shown earlier from Tutorials X is on the black ESP32. The BH1750 code from the first video is on the green Heltec Cube cell. I went to ably.io, which tells me about WebSockets. I learned about the UWS Micro WebSockets Node module. The code is on GitHub. However, I got the WS library client and server working first. The code I ran was modified example code from the API docs. You can see the packet sent to the client in the server. I also was able to look at Mozilla's documentation on the WebSocket API and find code that allowed me to write a client that interacted with my WS library server. Test.websocket.backup.html and test.websocket.html are examples of clients written with the Mozilla docs. Socket.send in the browser console allows me to send additional messages to the server. Here is the ESP8266 shop example that has been modified to use as a Node.js WebSocket server on the laptop. The more secure ESP8266 WebSocket library client on the Heltec LoRa ESP32 and a BH1750 code on the Cube cell. It also runs a client on a web server. Here's the sensor data on the web server via the phone. Here's some of the WebSocket traffic in Wireshark. This is not secure. I could try using a cryptographic authentication chip with asymmetric key cryptography to sign and verify the data, but this will not prevent eavesdropping. To do this, I will need to look at secure channels. Here's a WebSocket client code on the Heltec LoRa ESP32. Originally, I had PHP code written to get data, parse it, and write it to a database. I rewrote the code in JavaScript and call it from the Node.js server. I replaced the parser part of it with parser.js and parsedata.js. I made some modifications to the Node.js code and called the parser and wrote the captured data into the MySQL database. The database write seen in the shell is reflected in PHP my admin.